All right, let's take a look at these multiple choice questions. So for number one, we're looking at, in a recent survey, 81% of adults in a certain state have reported graduating from high school. If 15 adults from the state are selected at random, what's the probability that 5 of them have not graduated high school? So right now we want to write out our probability of graduating. Let's call that G, is 81%. We know we've got 15 people, and the probability of people graduating is 81%, but then we're looking at people not graduating. Specifically, we're looking at 5 of those. So like K is 5. So the opposite of graduating is not graduating. So that probability would be 0.19. And then show the right thing here. So here's what we've got. So then we're looking for not graduating, specifically 5 people within the 15. So right away I can eliminate these 3 because they don't have the correct combination of 15 total people, and looking for 5 successes. In this case, a success is not graduating high school, because that's what we're looking to examine. So for the next 2, D and E, they both have this correct, but now we want to see if they've assigned the correct number of successes and failures to the appropriate probabilities. So we're looking for 5 people not graduating. So we need an exponent of 5 on the 0.19, because that's our probability of not graduating, and that's happening 5 times, which then means 10 people will graduate. So D is the best option here. For the next question, we're just doing a little bit of interpreting. So for this one, the correct answer is A, but this time I want to think about why the other ones are wrong. So I'll just kind of talk through that. So for this one, we have a 94% of people have a certain characteristic. We have 45 people in a group, and then it says it's a binomial situation, and we have a mean of 2.7, and we want to interpret that. So first of all, A is correct because we have 45 people, and so our best prediction for another group of 45 people is that we would get 2.7 successes, or in this case, people, we're looking for people without the characteristic. So this has without the characteristic in there, that's the success, and this is an average we're looking at. And again, this average is computed based on the fact that we've got 45 people. So if I have another group of 45, the prediction I can make about people without the characteristic is that there would be 2.7 people in that group. So then for the rest of the options, I'll talk through D and E first, because those have the word until, which would be a geometric situation. Because this is specifically given to be binomial. So we're not looking at how many people do we pick until we get a success. That would be geometric, and we're doing a binomial thing here of just how many people have the characteristic in general and what's our prediction. So those are out for that reason. B is out because it has the word with, and we're looking at without the characteristic. And then as far as option C goes, every group of 45 people will have 2.7 people. So again, it's not a guaranteed number, but it's our average number that we would expect. It's not going to happen exactly that way every time, because every group of 45 will be a little bit different. There will be some variability there. So C is out for that reason. So for the next one, number 3, according to the 2015 census, 42.7% of Colorado residents were born in Colorado. The sample of 250 Colorado residents is selected. What's the standard deviation of the number of residents in the sample who were born in Colorado? So for this one, I have to decide, is this binomial? And if it is, there's a formula on our formula sheet that allows us to calculate the standard deviation of a binomial situation. So if I check bins, do I have a success and a failure? Yes, either you're a Colorado resident born there or not. One resident being born in Colorado would not influence the next one. So we have independence. We have 250 residents and a defined probability that, since we're going to assume those are the same, even if I picked, if I was really questioning 250 unique residents, the 10% condition would also tell me, like, okay, 250 residents is probably less than or equal to 10% all residents in Colorado that are Colorado born. So also because of the 10% condition, I know this is binomial in case I'm questioning, pulling out 250 people, that'll affect kind of my odds of having the same probability each time of being born in Colorado. But because of the 10% condition being satisfied, our sample's small enough that it's okay to do this. So in that case, I'm going to plug my information into this formula. And so that would be 250 times 0.427. Switching the percent of success into a decimal, and then 1 minus 0.427. So then just plugging that in on your calculator will get you your answer. So if we do that, I've got the square root of 250 times 0.427 times 1 minus 0.427. And that's going to give me an answer of 7.82, which is option B. All right, for the last multiple choice. Of all the fish in a certain river, 20% are salmon. So once a year, people can purchase a fishing license that allows them to catch up to 8 fish. So assume each catch is independent. Catching one fish doesn't influence your odds of catching the next one. Even if you're pulling one salmon out of a river, it's probably 8 salmon is less than 10% of all the salmon. Which of the following represents the probability of needing to catch 8 fish to get the first salmon? So thinking of it this way, it's like, I don't want to just catch 8 fish. I'm going to catch fish, and then the 8th one will be a salmon. So basically, I'm going to fail 7 times and not catch a salmon. But then on the 8th time, that last fish, I'm going to catch my salmon and be super happy about it. So this is a geometric situation because I'm waiting until the 8th one. So in that case, I'm going to have a failure 7 times. So in this case, a failure is going to be 0.8 7 times in a row, because it's 20% chance I get a salmon, so it's an 80% chance I get something else or nothing. And then here I've got the last one being that salmon. So multiplication, these are multiplied together and stuff. So this is this equivalent of option D. All right, let's look at the free response. For the free response, an orchard owner knows he'll have to use 6% of the apples he harvests for cider because they'll have bruises or blemishes. He expects a tree to produce 300 apples. So describe an appropriate model. We have to decide if this is binomial or geometric for the number of apples, cider apples, that may come from a tree. Justify your model by verifying appropriate conditions. So we want to basically decide, are we checking bins or are we checking bits? Is it geometric or is it binomial? So in this case, we're looking at how many apples we're going to get from a tree that we can then use for cider. So it's not like I'm going to pick apples until I get one I can use for cider. I'm going to pick apples and see how many out of that bunch I can use for cider. So we have an apple can be blemished or not. One apple is independent of the next in terms of blemishes. So one apple being blemished, we'll just assume doesn't, generally affect the next one. We have 300 apples, so a fixed number of trials, and a 6% chance of success, which is having a blemished apple we can use for cider. So this is a binomial distribution. And that would justify that. So explaining your bins. Those are the parameters that have to be met. And then for this one, it says, find the probability that there will be no more than a dozen cider apples. So a dozen is 12 apples. So I'm looking for no more than 12. So less than or equal to 12. So this is binom CDF. Because I'm looking at, you could have 1 blemish, 2 blemishes, but no more than 12 blemished apples. What's the chance? I have a dozen I can use for my cider. So we have 300 apples. Probability of success is 0.06 or 6%, and I'm looking at 12. And that's going to be binom CDF again, because you're looking at up to the 12. So second vars, and then we want to go binom CDF 300, comma, 0.06, comma, 12. So in this one, I'm going to have 0.085 probability of that happening. So about an 8.5% chance that I'm going to have no more than a dozen apples. So let's look at a few other probabilities. So I've got kind of the situation here at the top again, just so we remember how many apples we've got. For part C, it says, is it likely that there will be more than 50 cider apples? So this one we have to think about a little bit. So X being greater than 50. So on this one, I don't want anything below 50. So we're going greater than 50, strictly greater than, more than 50 cider apples. So in this one, what my calculator would give me is up to 50. So I could do binom CDF and figure out my odds out of 300 apples with a 6% chance of success, and choosing, what's the chance I get up to 50 apples that have blemishes. So first I could do this and figure out up to 50 apples. So if I plug that in on my calculator, I'm going to get a number. We're gonna try that again because I can't type. So 300, comma, 0.06, comma, 50. So the chance of that happening is like essentially 1. So you have 100% chance essentially of having somewhere between 0 and 50 apples that have blemishes. So remember, we want greater than 50. So we're kind of thinking of the opposite of this, meaning I want everything above what I just found. So 1 minus what I just found is a 0% chance. So yes, I would be surprised, because that shouldn't happen, having more than 50 blemished apples with this probability of success. For D, how many apples should the owner expect to be cider apples? So remember, expected amount is like your mean. So we want to find that. So N times P, if we have 300 apples and 6% of them are blemished, that's going to be my expected amount, or my mean, my average. So 300 times 0.06 is going to be 18. So we would expect 18 apples to be blemished out of 300. And then for part D, how much should the owner expect things to vary by? So we want to find the standard deviation. So if I do that, 300 times 0.06, then times 1 minus 0.06, which is 0.94. And I want to square root that. So I have the square root of 300 times 0.06 times 0.94. So we would expect this to vary by about 4.11 apples. So we expect, on average, the number of blemished apples, I'm going to run out of space, to vary by 4.11 from, and then the mean, you put their number there. Okay, for this one, it is estimated that 20% of health clubs with 3,000 members have high blood pressure. So we have 3,000 members, 20%, and then 150 health club members are randomly selected to have their blood pressure checked. Is this a binomial situation? So what we want to think about is that we have 3,000 members and we're choosing 150. And the issue here is that we would choose unique people. So if I pick a person and don't put them back into the pile of 3,000 people that I'm choosing from, I'm going to violate kind of my probability of success and my independence rule. But I have two conditions I can check to make sure it's still okay to use, that stuff. So the binomial stuff. So here we would say, if I check the bins, so I'm going to do a little scratch work here. So if I check the bins, I do have either you have high blood pressure or you don't. I have 150 people, so I do have fixed trials, but I have a without replacement situation. I'm going to select 150 unique people. So I'm not replacing the people, which is then going to affect my 20%. Because if I pull somebody out, look at them, then there's less people to pick from. There's also potentially less people with high blood pressure to pick from if I got one the first time. But our 10% condition, if it's met, still allows us to use the binomial formula and stuff to calculate things. So for this one, the 10% condition says I have to have, for the number of people I'm choosing, has to be less than or equal to 10% of, everyone I'm choosing from. So in this case, 150 has to be less than 10% of 3,000 people. There's 3,000 members at the health club. So 150 is less than or equal to 300. That's true. 300 is 10% of 3,000. So my sample's small enough that this is, these will be minimally affected enough to say that I can still use the binomial situation. So since the 10% condition is met, we can assume independence, making this a binomial situation. So we could show, obviously, this work to justify, and then we would say 150 is less than or equal to 300 as showing part of our work. So then for part B, we can go ahead and calculate two different ways, essentially using the binomial formula and doing it the normal way. So for the binomial formula, I already checked that I can use that from doing this question. So it's like, oh yeah, cool, my sample's small enough, I can do that. So let's do it. So it says that 35 or more of the health club members have high blood pressure. So again, on this one, I'm going to do binomial CDF. I know I have 150 people, comma, 20% chance of success, and it says that 35 or more. So on this one, it's a little tricky because we've got we want to find the probability that X is greater than or equal to 35. So on this one, we have to think a little bit. My calculator is going to give me up to 34, and then I can do 1 minus that to get what I want. So let's plug this in on our calculator first, because that's going to go from 0 up to 34. So 150.2 is the probability of success, and we're going to go up to 34 successes. So 34 people with high blood pressure. So I have 0.82% or 0.82 probability of getting that. So now I want 35 or more, and right now I'm up to 34 with this probability. So 1 minus this is going to give me everything above 34. So this is going to be 0.18. is my probability. Now I can do the same thing with the normal condition, but I want to check the normal condition property first, the large counts condition. So n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So for this one, we have 150 times 0.2, which is math I don't want to do in my head right now, which is 30, which is greater than 10, greater than or equal to 10. And then n times 1 minus p, so 150 times 0.8 is 120. So that's also greater than or equal to 10. So I can use the normal distribution to calculate this as well. So I could get a z-score, so on and so forth. So for this one, I'm looking at the mean, the expected amount here is n times p, which is 30. I'll have to find my standard deviation. So in this case, that's n times p times 1 minus p. So for us, that's the square root of 150 times 0.2 times 1 minus p is 0.8. So here is 4.9 that this varies by for my standard deviation. So then for me, what I've got is my z-score. So z equals, I'm going to go from 35 and up. So 35 or more. So 35 minus 30 divided by 4.9, which equals some number again. I don't want to do my head. So 35 minus a 5 divided by 4.9. It's almost 1, but so I've got a z-score of 1.02. I can go ahead and look that up on my chart, which I'm just going to pull this one up. So 1.02 is going to put me here. So 0.8461 is my area. And again, that's going to be this side. It's always the left-hand direction. I want the other side, so I'm going to do 1 minus that. And that's going to be my final answer, which is going to get me generally close to what this was.